We look up at the night sky. For centuries, we have felt a quiet, nagging certainty. Surely, we told ourselves, this vast and ancient galaxy is teeming with life. It is a simple, almost childlike assumption born from the sheer scale of the universe. Think about it. There are hundreds of billions of stars, and around those stars, hundreds of billions of planets. The math feels inevitable, doesn't it? But here is the crisis we have been trying to avoid for 60 years. We have pointed our most sensitive radio dishes at the heavens. We have built observatories that can detect a single photon of light from a world trillions of miles away. We have listened, we have looked, and the result is a silence so profound, so absolute, that it has begun to feel less like a mystery and more like a verdict. This silence is not an absence of data. Let me repeat that. It is the most important data point we have ever collected. It is screaming at us, but we have been refusing to hear it because its message is terrifying. The message is simple. Everything we assumed about where to look for life might be completely and utterly wrong. We have been searching for a signal from worlds like our own, from rocky surfaces sitting in the habitable zone. But what if that assumption is the very reason we find nothing? This is not a fun puzzle to solve over coffee. This is a reckoning. We must accept that our foundational assumptions, the very bedrock of astrobiology, may be built on sand. What if life does not need a surface? Think about that for a second. What if the most common type of planet in the galaxy, the gas giant, the massive ball of hydrogen and helium with no ground to stand on, is actually the most likely cradle for biology? What if we have been looking at the wrong kind of world this entire time? This film will not give you an answer to the Fermi Paradox. We are not going to wrap it up in a neat little bow. Instead, we are going to show you how data from a single NASA mission, a spacecraft orbiting a planet that has no surface, has forced a complete re-evaluation of the question itself. We are going to take you beneath the clouds of Jupiter, into a place where the pressures are crushing and the temperatures are hellish. And we are going to show you why the silence we hear from the stars might be the loudest warning we will ever receive. You know, the biggest question science has ever faced isn't about how the universe began. It is about why it is so quiet. We call it the Fermi Paradox, and it is a punch to the gut of our cosmic ego. Enrico Fermi, sitting with his colleagues over lunch back in the 1950s, looked at the numbers and asked a question that still haunts us. If the universe is so ancient, so massive, so full of potential, then where is everybody? That question has haunted us for 70 years. Let us remind ourselves of the scale we are dealing with. Our universe is roughly 13.8 billion years old. That is not a number the human brain was built to process. It is a length of time so vast that you could delete the entire history of Earth, every extinction, every mountain range that ever rose and fell, every single civilization that ever existed, and it would be nothing but a blink, a fleeting afterthought, a rounding error in the cosmic calendar. And in that unimaginable time, the universe has been busy. There are an estimated 2 trillion galaxies out there. 2 trillion. That is a 2 with 12 zeros after it. Each one of those galaxies holds somewhere between 100 billion and a trillion stars. So when you do the simple math, when you multiply 2 trillion by 100 billion, you get an absolutely absurd number of potential cradles for life. The raw numbers scream that life should be everywhere. It should be banging down our door. The fact that we sit here staring at a silent sky, listening to the hum of the cosmic microwave background radiation, the faint echo of the Big Bang, and nothing else, is not just an anomaly. It is a crisis. Over the decades, we have come up with some clever, even elegant solutions. But honest confession, they are all ideological positions dressed up in scientific language. There is the rare Earth hypothesis, which essentially argues that we won the lottery, that the formation of a stable, long-lived star, a rocky planet at just the right distance, a large moon to stabilize the axial tilt, plate tectonics, a magnetic field, a Jupiter to sweep up the killer asteroids, the specific chemistry of carbon and water, the sheer dumb luck of it all, means Earth is a freak accident, that life is a miracle precisely because it is so rare. Then there is the great filter. This one is darker. This one suggests that life is common, sure, but that there is a step in the evolutionary process, a wall, a barrier, that almost no species can get past. The terrifying part is that we do not know where the filter is. It could be behind us, meaning we have already survived the hard part. Or it could be in front of us, meaning our extinction is guaranteed, a natural consequence of our intelligence. It is the ultimate existential bet. And then there is the zoo hypothesis, which is frankly a little insulting. It suggests the aliens are out there, watching us, but they have agreed to leave us alone. We are a nature preserve, a cosmic petting zoo. They are observing us, taking notes, waiting for us to either evolve or self-destruct. These are all fun to think about. They make for great science fiction. But here is the uncomfortable truth. None of them are scientific conclusions. They are stories we tell ourselves to make the silence make sense. And the core of the problem, the reason these stories can never be proven, is the same flaw that runs through all of our reasoning. It is the Drake equation. Frank Drake wrote a famous equation on a blackboard in 1961. It looks like a powerful mathematical tool. It multiplies the rate of star formation, the fraction of those stars with planets, the number of habitable planets per system, the fraction where life actually appears, the fraction that develops intelligence, and the lifetime of a technological civilization. And it spits out a number for how many civilizations we might be able to talk to. Here is the problem, and it is a deep philosophical problem. Every single term in that equation is calibrated against a single data point, Earth. We know the rate of star formation from astronomy, but the fraction of planets that develop life, that is just a guess based on the fact that it happened here once. The fraction that develops intelligence, another guess based on the one example we have. We are not doing mathematics, we are doing autobiography. We have assumed with no evidence that life is a terrestrial phenomenon, that it needs a surface, that it needs to be like us. We have built an entire search strategy, billions of dollars of radio telescopes and space probes, on that assumption. We are looking for ourselves in the dark, and because we are only looking for ourselves, the only thing we will ever find is silence. We have trapped ourselves in a self-fulfilling prophecy. This brings us to 2021, and a paper that quietly, almost invisibly, shifted the entire ground of the argument. A team at MIT published a formal, peer-reviewed paper in the journal Astrobiology, revisiting a hypothesis Carl Sagan first wrote down in 1976. Sagan, always the visionary, had suggested that Jupiter might not just be a giant ball of gas. He suggested that its clouds might be alive, not just covered in life, but made of it, that the entire atmosphere, the churning, layered bands of ammonia, water and hydrocarbons, could host a stable, buoyant biosphere. The MIT paper was not fringe speculation. It was rigorous. It was mathematical. It was reviewed by the top minds in the field. It even caught the attention of NASA review panels. The framing shift is complete. We stop asking, why is space silent? And we start asking, what if life does not need a surface at all? What if the very thing we have used for 4 billion years to define a home, solid ground beneath our feet, is the very thing that makes us the exception, not the rule? What if intelligence, and even life, prefers to swim in a sea of air, free from the crushing gravity, the impacts, the tectonic violence of a rocky world? The statistical weight is staggering. The universe contains gas giants. They outnumber rocky planets by a ratio of 3 to 1. That is a vast, untapped demographic of potential life. We look for planets like ours because it is the only thing we can imagine. But the truth, the terrifying, wonderful truth, is that the universe is not constrained by our imagination. We have been asking the wrong question. For decades, we have looked out into the galaxy and wondered, where is everybody? The Fermi Paradox is a quiet scream in the dark. But maybe, just maybe, we have been searching the wrong rooms. We have been looking for blue marbles, for oceans and continents and a sky that looks like home. But what if life does not need a blue marble? What if it can thrive in a place we dismissed as a dead zone? What if it lives inside a storm? In 2016, a robotic explorer named Juno arrived at Jupiter after a 5-year journey. It was not sent there to find life. Nobody thought that was possible. The mission was designed to map the planet's magnetic field, to study its gravity, to peel back the layers of the largest world in our solar system. The scientists wanted to understand how Jupiter formed. They wanted to confirm the old models. They wanted to see a solid, compact core of roughly 10 Earth masses tucked away deep inside the gas giant. That was the expectation. That was what the textbook said. But Juno did something that makes scientists uncomfortable. It overturned those decades of planetary models. The gravity measurements came back, and they were weird. They were wrong, according to the theory. Instead of a dense, well-defined rocky core, Juno found a fuzzy core, a dilute, extended region where heavy elements are blended into metallic hydrogen. This structure is not compact. It is spread out, spanning roughly 50% of Jupiter's entire radius. Imagine an egg where the yolk is not a distinct yellow ball, but a slow gradient stretching all the way to the white. That is Jupiter's core. It is not a solid point. It is a smeared, messy interior. And this changes everything. The core accretion theory, the model that explains how our entire solar system formed, assumes that planets start as tiny pebbles of dust and ice that clump together into a solid core, which then pulls in gas. That is how we thought Jupiter was built. But Juno's fuzzy core suggests the process was not that clean. It suggests that Jupiter might have swallowed planetesimals whole, or that it formed through violent mergers, or that the core was eroded from the inside out. The implication is profound. If our understanding of how the biggest planet in the solar system formed is wrong, what else have we gotten wrong? How many other assumptions are baked into our models of distant exoplanets? We have been building a house of cards, and Juno just blew a hole through the ground floor. But that was only the beginning. Juno also detected internal waves. Oscillations inside Jupiter, analogous to seismic waves on Earth. These wave patterns confirmed something we had only guessed at before. Convective movement. Material rising and falling along vast columns that stretch from the outer atmosphere deep toward the core. Jupiter has internal weather. It is not a static ball of gas. It is a dynamic churning engine. The atmosphere does not just sit there. It reaches down, way down, and mixes with the interior. We are talking about weather that goes 3,000 kilometers deep. The banded structure of Jupiter, those beautiful stripes we have seen in photographs for centuries, they are not a thin shell. They are the visible tip of an enormous layered ocean of gas, hundreds of times deeper than the deepest ocean on Earth. And then the microwave radiometer did something incredible. It penetrated the ammonia cloud layer. For the first time, we saw what lies beneath the visible surface. The banded structure extends at least 3,000 kilometers down. The atmosphere is not a thin shell. It is a dynamic, layered ocean of gas, hundreds of times the depth of Earth's oceans. We thought the clouds were just a colourful skin. They are not. They are the surface of a vast hidden world. And here is where it gets personal. Juno measured the temperature gradients in Jupiter's atmosphere. About 50 kilometers below the cloud tops, there is a zone where the pressure is between 1 and 10 atmospheres. That is the same pressure range we experience at sea level on Earth. And the temperature? It ranges between 0 degrees Celsius and 100 degrees Celsius. Those are terrestrial conditions on a gas giant, a place we assumed was a frozen hostile wasteland. But there it is, a habitable band. A layer of the atmosphere where the temperature and pressure are exactly right for liquid water to exist. And there is water there, water vapour, ammonia, organic compounds, and lightning, continuous lightning. Juno detected thousands of strikes per hour in that region. That is an amount of energy comparable to Earth's most powerful thunderstorms. And lightning is more than just a light show. On early Earth, lightning is thought to have been a primary driver of prebiotic chemistry. It provides the energy needed to assemble the building blocks of life. The Miller-Urey experiment proved that. So here we have a place with the right temperature, the right pressure, water, organic compounds, and a constant electrical spark. What else do you need? In 2021, a study led by MIT formally modelled what life would require to exist in this zone. They asked the hard questions. How would an organism stay aloft in an atmosphere with no solid ground? How would it avoid being dragged down into the lethal high-pressure regions below? How would it tolerate the sulfur and ammonia chemistry that would be toxic to most Earth life? The paper concluded that none of these conditions are definitively prohibitive. It is possible. It is plausible. The environment does not rule it out. But let me be very clear. Juno found no life. It found the conditions compatible with life. That distinction is the entire point of this documentary. We are not saying there are Jovian jellyfish floating in the clouds. We are saying we can no longer pretend the possibility is absurd. We built this massive spacecraft, sent it to the most inhospitable place we could think of, and it found a habitable zone. It found a place where life could, in theory, exist. And if it could exist there, on a gas giant 500 million miles from the Sun, then what about the billions of other gas giants in the galaxy? The ones we have been ignoring because we thought they were dead ends? We have been looking for Earth 2.0. But maybe we have been looking in the wrong place. Maybe the universe is not filled with blue marbles. Maybe it is filled with gas giants, each one holding a hidden layer of warmth and lightning and possibility. Juno has not answered the Fermi Paradox, but it has handed us a new question. What if we are not alone, because we are not looking where they are? That brings us to the implications. And this is where the story gets really strange, because the idea of life floating through the clouds of a gas giant is not new. It is, in fact, one of the most hauntingly beautiful scientific hypotheses ever proposed. In 1976, two of the greatest minds in the history of science, Carl Sagan and Edwin Salpeter, published a paper that was so far ahead of its time it practically vanished into a black hole of academic indifference. The paper was titled Particles, Environments and Possible Ecologies in the Jovian Atmosphere, and it appeared in the Astrophysical Journal supplement. Most people have never heard of it. Even many astronomers have only a vague recollection. But what Sagan and Salpeter did in that paper was, in a very real sense, paint a picture of a world that we are only now beginning to see with our own instruments. They described three hypothetical types of Jovian organisms. First, the sinkers. These were tiny, almost like spores or seeds, designed to drift downward through the atmosphere until they hit a level of temperature and pressure that was comfortable for them. Then you had the floaters. And the floaters were the showstoppers. Sagan imagined these as enormous gas bag organisms. Think of a hot air balloon but alive. They used hydrogen for buoyancy, and they were massive, truly massive. Sagan calculated that to maintain a stable position against the brutal convective downdrafts of Jupiter's atmosphere, a floater would need to be the size of a city. We are talking kilometers across, blobs of organic matter, miles wide, drifting through the ammonia clouds like lazy whales through a stormy ocean. And then there were the hunters. This is where it gets creepy. The hunters were the predators. Sagan and Salpeter figured that if you had these enormous slow-moving floaters, something would evolve to eat them. The hunters would be fast, agile, and probably electrical. They hypothesized that hunters would use charged particles to stun or kill their prey, turning the lightning storms of Jupiter into a hunting ground. For 40 years, this paper sat on the shelf. It was a beautiful thought experiment, a scientific fantasy. But nobody took it seriously as a testable hypothesis. There was no way to prove it wrong, and no way to prove it right. The technology simply did not exist. But that changed, and it changed fast. Three things happened that dragged the Sagan hypothesis out of the dusty archives and back into the light. First, Juno arrived. The data on Jupiter's atmospheric composition was far more detailed than anything we had before. We started seeing complex organic chemistry, water cycles, and pressure-temperature gradients that looked suspiciously habitable. Second, the science of extremophile biology exploded. We discovered life living in acid, in boiling water, in the frozen darkness of Antarctic rock, under the crushing pressure of 7 kilometers of ocean. The envelope of what biology can tolerate was torn wide open. And third, in 2020, there was the phosphine detection on Venus. You remember that, right? The discovery of phosphine in the clouds of Venus was a bombshell. Because phosphine is a biosignature. On Earth, it is almost exclusively produced by microbes. Suddenly, the scientific community was having a very public, very serious debate about whether there was life floating in the clouds of our sister planet. It was not dismissed, it was debated in peer-reviewed journals. It was real, and that changed everything. It meant the old reflex, the automatic dismissal of any atmospheric life hypothesis, was gone. The door was open. And if the door was open for Venus, why not for Jupiter? So, what are we really talking about here? We are talking about the possibility that biology on Jupiter does not use water in the way we think of it. Water is great for life on Earth, but it freezes in the cold of the outer solar system. Ammonia, on the other hand, is a different story. Ammonia is liquid across a much wider range of temperatures, and it is abundant in Jupiter's clouds. It is a speculative idea. We have no evidence for an ammonia-based biochemistry, but we also have no evidence against it, and the extremophile research has shown us something profound. Life does not just survive in hostile environments, it thrives. It adapts, it expands. There are organisms on Earth that live in pools of sulfuric acid with a pH of 0. There are organisms that live inside solid rock, eating minerals. There are organisms that can withstand radiation doses that would kill a human in seconds. If life can do that here, on this tiny rocky planet, what could it do in the endless, warm, chemically rich atmosphere of Jupiter? What would a creature look like after 1 billion years of evolving in a three-dimensional world without a solid surface? It would not look like anything we have ever seen. It might not even be what we think of as a creature. It might be a layer, a living layer of the sky itself. And this is where the Sagan hypothesis becomes something more than just an interesting idea. It becomes a weapon against the silence of the universe. Think about the Fermi Paradox. The question is, where is everybody? The traditional answers have always focused on planets like ours, Earth-like worlds, blue marbles. But what if we have been looking in the wrong places? What if the most common habitat in the universe is not a rocky surface, but a gas envelope? Gas giants are everywhere. They dominate the statistics of exoplanet discoveries. They are the most common type of planet in our galaxy. And if life can exist in the clouds of a gas giant, then the universe is not silent. It is screaming. We just could not hear it because we were staring at the ground. The Sagan hypothesis is no longer a thought experiment. It is a testable scientific question. The data we have from Juno does not rule it out. The chemistry is there, the energy is there, the stability is there. All we are missing is the confirmation. And that confirmation might come sooner than you think. The next step is not just to look at Jupiter. It is to look at the atmospheres of exoplanets, to search for biosignatures in the spectral lines of distant gas giants, to see if there is a pattern, a chemical imbalance, a flicker of something that should not be there. We are standing on the edge of a new kind of biology, a biology of the air, and if it is real, then the Fermi Paradox does not have a tragic answer. It has a beautiful one. We are not alone. We were just too busy looking down to look up. The numbers we have been working with are already staggering. 2,000 known gas giants within 300 light-years of Earth. That is not a guess. That is a confirmed count from existing surveys. And when we scale that up to the entire Milky Way galaxy, the estimate balloons to something almost impossible to hold in your mind. 100 billion gas giants. Let that sink in for a moment. 100 billion worlds, each one a potential ocean of atmosphere, a domain of layered clouds and shifting pressures and temperatures that could, just could, harbour life. And yet, for decades, we have pointed our most powerful telescopes at a very different kind of target. Rocky planets. Small, solid worlds orbiting within the so-called habitable zone where liquid water might pool on a surface. We have built our entire strategy for finding life out there on the assumption that life needs a place to stand. We look for oxygen because Earth has oxygen. We look for methane because microbes produce methane. We look for water vapour because water is the solvent of life as we know it. And all of that makes perfect sense, except it also makes us blind to anything that does not fit the pattern. Think about the James Webb Space Telescope. JWST is the most powerful space observatory ever built. Its ability to perform transmission spectroscopy, to analyze the chemical makeup of an exoplanet's atmosphere as it passes in front of its star, is nothing short of revolutionary. But here is the thing. The early targets for JWST, the ones that grabbed the headlines and the observing time, were almost exclusively rocky worlds. TRAPPIST-1 and its system of 7 Earth-sized planets, LHS 38844b, a handful of others. These are the planets we desperately want to understand because they look familiar. Meanwhile, gas giants like WASP-39b and HD WEN 9733b were studied, yes, but primarily for atmospheric physics, for understanding weather patterns and cloud composition and the mechanics of extreme worlds. Not for biology. Not once did a team of astronomers schedule a gas giant observation and say, "Let us look for the spectral signature of alien life floating in that hydrogen sky." That simply was not on the table. Not because it is impossible, because it never occurred to us. But in 2022, a team at the University of Edinburgh published a paper that flipped the script. They proposed that JWST, if pointed at the right gas giant and given enough observing time, could actually detect biomass signatures in the atmosphere. Imagine looking down at Earth from orbit and seeing the green bloom of algae across an ocean. That is the analogy they used. If the organism density in a gas giant atmosphere is high enough, if it forms vast floating colonies of microbial or even macroscopic life, the spectral fingerprint would be detectable. It would show up as an absorption feature, an unexpected band of light being eaten by something alive. The paper was careful, it was rigorous, and it ended with a quiet, devastating observation. We have never designed an instrument specifically to search for this. Not one telescope, not one mission concept, not one line item in a space agency budget has ever been dedicated to the search for aerial life. We have built instruments to find water on Mars. We have built instruments to sniff the plumes of Enceladus. We have built instruments to map the surface of Europa's ice. But we have never built a single device whose sole purpose is to look for life floating in a gas giant atmosphere. That is a gap in our imagination, and it may be the gap that explains everything. Now let us take this to the next level. The SETI paradigm, the search for extraterrestrial intelligence, has been operating on a fundamental assumption for over 60 years. It is radio-based. We listen for signals. We scan the stars for narrow-band transmissions, for the kind of deliberate artificial radio leakage that our own civilization produces. But think about the kind of civilization that would evolve inside a gas giant. There is no surface. There is no solid ground. There is no place to anchor a radio tower. There is no bedrock on which to build a transmitter. A Jovian civilization would be pressure adapted. It would be a civilization of organisms that live in a continuous, fluid medium, where the atmosphere itself is their ocean, their sky, their land, their everything. Communication in such an environment would not happen through electromagnetic waves travelling through vacuum. It would happen through acoustic signals, through chemical gradients, through pressure waves, through something we cannot even imagine. They would have no reason to develop broadcast technology aimed into space, because space is not their environment. Space is a vacuum, a hostile, empty, silent void that would kill them instantly. Why would you shout into a vacuum you can never visit? Why would you build a radio telescope when you have never touched metal or mined an ore or stood on solid ground? A Jovian civilization would be distributed. It would be collective. It might be a single sprawling consciousness spread across millions of cubic miles of atmosphere, connected by chemical signals that propagate at the speed of sound. It would not be a civilization of individuals building cities. It would be a civilization of life, thinking together, moving together, existing as a fluid intelligence in a fluid world. And it would produce absolutely no radio leakage that we know how to detect. None. Zero. The universe could be teeming with such civilizations, and our radio dishes would hear nothing but the hiss of cosmic background radiation. We designed SETI to find ourselves. That is the uncomfortable truth. We built a search strategy based on the assumption that intelligent life must look like us, think like us, build like us, and broadcast like us. And if that assumption is wrong, then the silence of the universe is not a silence at all. It is a roar of life that we simply cannot hear. The universe is not empty. We have been listening on the wrong channel, and we have been looking at the wrong worlds. The false limit. It sounds almost like a contradiction, doesn't it? A limit that isn't really a limit, just something we've put in place in our own minds. That's exactly where we find ourselves now, standing at the edge of what Juno has actually shown us, and trying to separate the data from the dreams. Let's be brutally honest from the start. The Juno mission scientists have been incredibly careful. Not just careful, almost painfully so. They have gone out of their way to say that nothing, absolutely nothing in the data confirms or even suggests the presence of life. Nothing. They have been very clear on that point. What the data does show, however, is something that makes the hair on the back of your neck stand up just a little. It shows conditions that are compatible with certain kinds of biochemistry. That's the word, compatible. Not proof, not evidence, just a quiet mathematical compatibility. And we're going to honour that distinction throughout this entire story, because the difference between compatible and confirmed is the difference between a hunch and a headline. So let's look at what that compatibility actually means. The habitable band, that sweet spot in Jupiter's atmosphere, where temperatures and pressures might be just right, is not a calm place. It is not a tranquil ocean of gentle clouds. It is, in the words of the scientists who study it, extremely dynamic. That's a very polite way of saying it is a violent, churning chaos. Convective updrafts scream upward with the force of a hurricane, and downdrafts, just as powerful, slam massive volumes of gas back down toward the crushing depths. For any organism to survive here, it would not just need to float. It would need active position control, constant, deliberate, costly effort, just to stay in the zone. The energy cost would be enormous. And we haven't even talked about what is coming from above. Juno's ultraviolet measurements painted a truly grim picture of Jupiter's upper atmosphere. The entire region is being relentlessly pummeled by ionizing radiation from the planet's magnetic field. We are talking about one of the most intense radiation environments in the entire solar system. It is a brutal, sterilizing barrage from above. The habitable band sits just beneath this hellish layer, partially shielded, but the interface between the two is hostile beyond anything we have on Earth. It is like trying to live right below the rim of an active volcano. And to make matters worse, those famous ammonia clouds are not stable structures. They are not great permanent floating islands. They form, they dissolve, and they reform on timescales that would make your head spin. Hours to days. Any aerial ecology would need to be incredibly robust, capable of surviving radical, rapid environmental shifts that would destroy most earthly life in a heartbeat. This is where the skepticism kicks in, and we have to be fair about it. Planetary scientist Kevin Stevenson has looked at the numbers, and his conclusion is sobering. He argues that the energy budget simply does not close. Maintaining position against Jupiter's overwhelming convective energy output would require more metabolic power than any known biochemistry can supply. He is saying the math does not work. It seems impossible. But here is the thing about impossible. It has a funny way of being wrong. The exact same criticism, the exact same argument about energy budgets was levelled against the idea of life at deep-sea hydrothermal vents on Earth. Before 1977, the scientific consensus was that nothing could survive down there. The pressure was too great, the darkness absolute, the chemical environment too harsh. The textbooks said it was impossible. Then the submersible Alvin descended, and the lights of the Alvin illuminated a thriving ecosystem of giant tube worms, crabs and bacteria living in water hot enough to melt lead. Biology found a solution no theorist predicted. Life found a way where the math said no way could exist. So let us sit with that for a moment. Skepticism is healthy. It is the foundation of science. But history has a nasty habit of humbling us. It warns us time and time again against dismissing possibilities based on incomplete models. The models we have for Jupiter are brilliant, but they are also guesses. Informed guesses, but guesses nonetheless. We are looking at a world we can only barely touch, and we are trying to tell it what is and is not possible. Maybe that is the ultimate false limit. Not the one Jupiter sets, but the one our imagination imposes. Saturn, for example, has its own version of that temperate band, and it is every bit as strange. When the Cassini spacecraft spent years orbiting the ringed giant, it detected something in the upper atmosphere that the textbook simply did not predict. Complex organic chemistry. Molecules that, by all logical accounts, should not be there unless something is actively making them. Now, the standard explanation is photochemistry, sunlight driving reactions in the atmosphere. But here is the thing. We have seen these molecules pop up in conditions where photochemistry alone does not quite add up. It is as if the atmosphere itself is cooking up compounds that require a nudge, a biological nudge, to explain their abundance. And we cannot just wave that away. We have to sit with the discomfort of not knowing. Then there is Titan, Saturn's largest moon. Titan is a world that should be frozen solid, locked in an icy deep freeze forever. Instead, it has methane lakes, organic rain, a nitrogen-rich atmosphere thicker than our own. It rains there, it rains methane, and when that methane rain hits the surface, it carves rivers and carves deltas, just like water does here on Earth. But the real kicker, the part that keeps astrobiologists up at night, is what forms in its hazy orange sky. Scientists call them tholins. These are complex organic molecules, the kind of prebiotic building blocks that, under the right circumstances, could lead to something more. Tholins form when radiation from the sun and cosmic rays slam into nitrogen and methane, and they produce a rich, goopy soup of organic material. We have confirmed this. It is real. It is happening right now, millions of miles away, on a moon that we can barely see as a dot in our telescopes. And if Titan can produce that much organic chemistry, what might be happening in the clouds of gas giants, where the conditions are even more stable, even more temperate? Uranus and Neptune, the ice giants, remain largely a mystery. They have been visited only once by Voyager 2, a flyby that gave us incredible images but not enough time to answer the big questions. We know they have atmospheres. We know they have bands, temperature layers, and weather patterns. But we have not systematically evaluated those bands for habitability. We do not know if there is a layer, like Jupiter's, where the pressure and temperature are just right, and where organic molecules could thrive. That is not a knock on the scientists. It is just a fact. We have not looked. And that is one of the most frustrating truths in planetary science right now. The 2030s are going to be pivotal. NASA has a proposed Uranus orbiter in what they call Phase A study, which means it is being seriously considered. The JUICE mission, the Jupiter Icy Moons Explorer, is already on its way to study Europa, Ganymede, and Callisto. But here is the catch. None of these missions carry instruments designed to detect life in the atmosphere. They are looking for signs of habitability, sure, but they are not sniffing the air for microbes. They are not sampling the clouds. That is a huge blind spot. We are sending spacecraft to the most promising worlds in the solar system, and we are not packing the one tool that might actually answer the question of whether we are alone. Now, zoom out, way out. Exoplanet demographics from Kepler and TESS have revealed something that upended everything we thought we knew about planetary formation. The most common type of planet in the galaxy is not a rocky world like Earth, and it is not a gas giant like Jupiter. It is something in between. We call them sub-Neptunes. These are worlds with a radius somewhere between Earth and Neptune, and they are everywhere. They dominate the galaxy, and they likely have hydrogen-rich atmospheres, thick and puffy, with pressure and temperature bands that could be habitable. We have no missions to study them for biology. None. Zero. We are flying past the most abundant type of planet in the universe without a plan to look for life. The true limit is not the universe. It is not the vastness of space, the distances, the radiation, the cold. The true limit is our imagination and the instruments we design. We have built machines to confirm what we expect to find. We set spectrometers to look for water, for methane, for carbon dioxide, the molecules we know. But we do not send instruments that can sniff out the unexpected. We do not build telescopes that can see the weird, the strange, the stuff we have not even thought of yet. We are travelling the cosmos with a checklist written 100 years ago, and we are refusing to look where the light is weird. That is the real false limit. Not the one Jupiter sets, the one we impose on ourselves. And this brings us to the heart of the matter. The Fermi Paradox, that famous question, where is everybody? Rests on a foundation poured in the 1950s. Back then, the assumption was simple and, I think, a little arrogant. Any advanced civilization would eventually start blasting radio waves across the galaxy, just like we did. They assumed technology would look like our technology. They assumed ambition would look like our ambition. But here is the thing. They made these assumptions before we had any clue about the sheer mind-bending diversity of possible biospheres. Before we understood that a planet is not the only game in town. We usually imagine the Great Filter as a catastrophe, war, environmental collapse, self-destruction wearing 1,000 different masks. It is a grim thought, and it dominates a lot of the conversation. But what if the filter is not a bang or a whimper? What if it is geography? Think about that for a second. If most life in the universe exists in environments where building a spaceship is not just hard, but physically impossible, then the Great Silence makes perfect sense. No one is stopping the aliens. They just cannot leave. Imagine a civilization living deep inside a gas giant. No solid surface to build a launch pad. No vacuum to aim a rocket at. They have never seen a star. They have never seen the sky. The very concept of outside might not exist in their language. The filter is not destruction, friends. It is the total absolute absence of any motivational mechanism to get off your cosmic island. They are not dead. They are not hiding. They are simply trapped. This reframing of the paradox is powerful because it dissolves the whole thing without needing rare Earth theories, without expecting every species to blow itself up, and without explaining silence as some grand alien conspiracy. The universe could be absolutely teeming with life, complex life, intelligent life, ancient life, but it is structurally invisible to every single search strategy we have ever deployed. Every radio telescope pointed at empty space, every optical scan for laser pulses. We are looking for neighbours who might not even have a door to knock on. Now, let me bring in a piece of science that makes this more than just a philosophical daydream. NASA astrobiologist Sarah Walker has been working on something called assembly theory. Published in Nature in 2023, her framework proposes that life can be detected by the sheer complexity of molecules, regardless of the biochemistry involved. It does not care about carbon versus silicon. It just looks for the fingerprints of selection, of evolution, of assembly. In theory, this would work perfectly on a gas giant. You just need a way to grab a sample and analyze the molecular chaos. But here is the cold, hard truth. No probe has ever been sent into Jupiter's habitable band with instruments designed to look for biological indicators. The Galileo probe descended into Jupiter in 1995. It transmitted data for exactly 58 minutes before the pressure crushed it at 22 atmospheres. That is not even close to the zone where we think life could exist. That is like dipping a bucket into the ocean a few inches from the shore and declaring the sea is empty. A dedicated atmosphere probe designed to float down to that sweet spot between 1 and 10 atmospheres, to sample the chemistry, to look for biomass indicators, to listen for electromagnetic chatter from within that alien ocean. It does not exist. It has been proposed to space agencies, twice in the last decade, rejected both times. So I want you to hear the final words of this film, and I want you to really sit with them. The question this film asks is not, is there life in Jupiter? That is unanswerable with current data. The question is, have we designed our search for life around what we hoped life would look like? And if so, what have we missed? We have come full circle. We began this journey with an image of the Milky Way hanging in the void, and that image is with us still. The silence between the stars, that great and terrible quiet, has not been broken. But if you have been listening, if you have really been paying attention, you know that we now hear that silence differently. It is no longer a verdict, a cold judgment that we are alone. It is a question, and that question has been redirected, pointed squarely back at us. What are we missing? What are we unwilling to see? The truth is, the technology to find an answer is within our grasp. We have the data. We have the evidence. From the swirling high-pressure oceans of Jupiter to the strange chemistries simmering on moons we once dismissed as dead. We know now that we have been asking the wrong questions. We searched for a reflection of ourselves, for oxygen, for water, for the precise chemical thumbprint of life on Earth. But the cosmos does not owe us a mirror. We lack the will. We lack the courage to build the instruments that look for life we do not even recognize. Life that breathes ammonia, life that swims in methane, life that exists in forms so alien it would rewrite our textbooks overnight. The search continues. It has to, but the map must be redrawn. Every assumption we carried into this century is now suspect, and that is a beautiful thing. It means we are still beginners. It means the universe still has secrets. If you want to see more explorations like this, investigations that respect the data while challenging the very assumptions we hold most dear, then subscribe to This Is Space. The universe is waiting for us to ask the right question. So look up, look closer, because the answer has been there all along, hiding in plain sight, waiting for us to finally open our eyes. And now we let the silence speak one last time. Earth from above, a pale blue dot in an ocean of infinite possibility. And then, slowly, that light fades to black,